This lesson is about linear equations in one variable. Here's an example. Before we solve this algebraically, let's talk about what it means for a number to be a solution to the equation. Imagine I were to put a 2 where x is. I'm not saying that this is how you would solve the problem, but imagine I put a 2 in place of x. Would I have a true statement? Well, I wouldn't, because 3 times 2 is 6, and 6 plus 1 isn't 9. There isn't 19 either. And so, this statement is false when x is 2. But what if I were to put a 6 where x is? Well, I would have a true statement, because 3 times 6 is 18, and 18 plus 1 equals 19, and 19 equals 19 is true. So we can see that there are certain x values that make equations true, and there's certain x values that make them false. For a number to be a solution, we're specifically looking for the numbers that make the equation true. But you don't want to guess. You'd rather have an algebra strategy that you can count on. So how do we solve such an equation? Well, there's a rule that guides equation solving. It states that we can do any math operation to both sides of an equation. Okay, well, if I can do any math operation to both sides, can I add 7 to both sides? Well, let's examine what would happen if I did. If I were to add 7 to both sides, I would get this statement. That statement is no simpler than my original problem. Can I add 7 to both sides? Absolutely. Is there a reason to? No, it served no purpose. It didn't make my equation simpler. I like to call this valid and useless. It's valid because I followed a math rule correctly, and it's useless because it didn't serve any purpose. So if adding 7 doesn't serve a purpose, let's see how subtracting 1 would serve a purpose. Subtracting 1 from both sides cancels the 1's because 1 minus 1 is 0. And now I have a simpler equation than I had to start with. Now, at this point, it would be advisable to divide both sides by 3. I can do anything to both sides of this equation. Why did I choose to divide by 3? Well, because it got the x by itself. After all, if you look at the left side of the equation, 3x divided by 3, that's just x. Because 3 times any number divided by 3 is that number, and therefore the 3's essentially cancel, and that gives me the solution to the problem. Let's look at a more complicated situation. I can do anything I want to both sides of this equation. Why don't I subtract 1? It worked great on the last problem. Well, it's not likely to work here. Am I allowed to subtract 1? Absolutely. Should I? I don't see why I should. It wouldn't cancel anything out or make the equation simpler. By contrast, however, adding 5 would cancel something out and therefore make the equation simpler, so I think that's a good choice. By the way, subtracting 4x would also cancel something out and make the equation simpler, so that's not a bad choice either, but I'm going to go back to my choice of adding 5. If I were to add 5 to both sides, the negative 5 plus 5 would be 0. 4x plus 0 is 4x. And this gives me a simpler equation than the one I started with. That is your ultimate goal when applying the do anything to both sides rule of algebra. Now, if I were to want to simplify this equation further, could I add 21 to both sides? Well, I could, but I don't think it would simplify things. It would cancel out the negative 21 on the right side, but the left side would just equal 4x plus 21. Those are not like terms and therefore not combinable. So am I allowed to add 21 to both sides? Yes, but I don't think I will. I think I'll subtract x instead, because that will actually make my equation simpler. By subtracting x, x minus x becomes 0, and I now have a much simpler equation than any of the ones above it. At this point, I could choose to look at these and talk about why I made those choices in the first place. I like to make choices that separate the x terms from the constants. By that I mean these choices led for my x terms to all be on the left and my constant terms, the terms without x's, to be on the right. So that's what motivates my choices. At this point, I could divide by -21, but I don't think that's advisable because I want to get x by itself. Rather, dividing by 3 is a good choice because that will isolate x and tell me my solution to the problem. You can see on this and the previous problem that we started out with this rule I've typed in purple, the do any operation to both sides rule. But that's not always your first strategy necessarily to achieve success on a solving problem. This problem is different. Notice that one of the sides is simplifiable. Well, which side is simplifiable, the left or the right? Is the right side simplifiable? No, it turns out that's not because they're not like terms. But this side, the left side, is simplifiable. Let's focus on that for a minute. We're not solving here. I'm just simplifying the left side of the equation. To do that, I could distribute the 3 into the parentheses and then combine my like terms. -6 plus 13 is 7. And that doesn't solve the problem, but what that does is it makes the left side of the equation simpler. Notice I didn't do anything to both sides. I simply modified one of the sides of the equation to get a simpler equation because I could. But now that each side is as simplified as it can get, let's think about doing something to both sides that will simplify matters. Remember, my overarching goal is to get my x terms on the left side and my constant terms on the right. By the way, that's not mandatory. Other videos and professors will do it differently, but I like to, for consistency's sake, always get my x terms on the left. It's easier for me to follow the same routine every time. Well, to get only x terms on the left, it would be smart to subtract 7, because 7 is a constant term. And if I subtract 7, 7 minus 7 is 0, and that simplifies my equation. And that is your goal when doing something to both sides. Now, to simplify this equation further, I think adding x to both sides would be a great idea because that gets rid of my variables on the right and essentially puts all my variable terms on the left. And after that, I can simply divide by 4, and the 4's on the left will cancel, and x will equal whatever 1 divided by 4 is. Well, 1 divided by 4 is 1/4. Note, you can have fraction answers to these problems. That shows most of the information that you'll need, but before we conclude, let's examine some unusual cases. Now, these problems may not look unusual, but it turns out one of them has all numbers as its solution, and one of them doesn't have a solution at all. Let's look at this first one. What do I mean it has all numbers as a solution? There's nothing about the problem that would indicate that on first glance. Well, it turns out, and we'll see why in a minute, but it turns out that this is a problem that if you plugged in literally any number for the x's, you would get a true statement. But to see why that is true, let's pretend that we didn't know that. Pretend you don't know the answer to this problem, and let's just start solving it using the techniques from earlier in this video. I would distribute the 2 to the parentheses, and then combine my 6 and my 1 as my like terms. Now do you see why this is an all numbers problem, meaning any number for x would be a solution? Because this equation says 2x plus 7 equals 2x plus 7. Isn't it true for any number that 2 times that number plus 7 is the same as 2 times that number plus 7? Well, that's the justification for this being an all numbers problem. But if you don't see it yet, let's proceed. Let's use the same techniques from the previous slide as if we didn't know anything was unusual here and we're continuing to solve. I could subtract 2x from both sides and my variables would cancel out. Now when your variable cancels out and you get something like 7 equals 7, that does not mean that 7 is the answer to the problem. That means that the original problem is true for any x for which 7 equals 7 is true. Let me rephrase that. 7 equals 7 is always true. Therefore, the original equation is always true. And if you really want to see that that's the case, pause the video, pick some totally random number for x, plug it into the original problem, you will get a true statement. Let's go to this problem. This problem turns out to have no solution. That means there is no number x that would make this a true statement. But you wouldn't know that by looking, so let's pretend we didn't know that was the case and just solve as usual. I would distribute the 2 to the parentheses. I would combine like terms to simplify the right side as much as possible. At this point, you can kind of see why this is a no solution problem. After all, this bottom line is saying 2 times some number plus 7 equals 2 times that same number plus 19. Now, if you can see why this is the case, then you understand that it's a no solution problem and you wouldn't write any more past this. But if you don't see why let's just continue to solve this problem like we normally would. Maybe I would subtract 19 to cancel out the 19. Maybe I would then subtract 2x. But at one point, you're going to get a false statement. Now, this bottom line does not mean that negative 12 is the answer, and it does not mean that 0 is the answer. It means that the equation has no solution. Because for the equation to have a solution, it would have to be true that negative 12 equals 0. Negative 12 can't equal 0, therefore the problem can't have a solution. To summarize, whenever you get a unilaterally true statement like 7 equals 7 without a variable, all numbers would be your solution in this rare case. In the other rare case, if you get a unilaterally false statement like negative 12 equals 0, that indicates that your equation has no solution. This concludes the lesson.